Okay, hello. So today I just finished last night grading score. Average is, I forgot the average. Let me check the average. Okay, let me check the average. I put it in my notes here. Okay, we have. Okay, average is 48. 48. The average score for 48. 48. I would like to announce later what we can do, and then you can also maybe after around 1 hour I will deliver your score. So let me just continue a little bit on our sections. Just finish off the first part of introduction of the definite integral. Okay. So last time we solved the derivative or the integration, definite integration, using the definition by taking the sum. Okay. So we see that the result is negative. This is because when we are taking the area under the curve, like in this one here, the under the curve means how the curve relate to the axis. For example, this one, the under the curve is this, okay, which we call this is the positive, right? It's positive result. But here, this is also under the curve. If you see from different perspective, right? It's under the curve. So we need to relate all with the x, okay? So we say that this green color is negative, which means if we get negative result, it means that this green is much more bigger than the red one, okay? And then I would like just to review a little bit. This is last time. This is last time with I think with a clear statement. So this is the definite integral definition. And this part here, the right part, is the sum. Or later we can see that the sum, we can use several methods for calculation or for some numerical methods. So what basically this means is, if we want to evaluate this whole area, we can define this area with some rectangle. And we can take the rectangle, we can have, last time we have the right endpoint, the rectangle, the right side is touching the curve, or in general, we can just take it anywhere, and we say that this will be the one that is on the point in the curve. The point in the curve was, we call the sample point. To make it applied in every point in the curve. Okay, so we call this as a sample point. Okay, so we have these definitions. And then this is the graph of the last discussion, which we can see that the area down here is bigger, which means it's getting the negative results. And if you see, in general, whenever you have the area below the x-axis and it is, we can say it's under the curve, we can take this as a negative sign. Okay? And we are going to add all this area. So plus, minus, plus. Okay? And if we see, if we approximate this area, if we approximate with some rectangle, and you see that, of course, this has been done with some software. So as n increase from 40 to 5,000, you will see that our exact answer from the definite is 6.75. When n is 40, it's still 6.39. So it's still long way to go. So after we get 5,000, we get closer to 74. Okay? So it means that our approach for n getting larger, and maybe if we take limit as n getting closer to infinity, was correct. It was correct, and then this could approach this number. Okay. So that's just a little bit review from what we have discussed. And then the theorem, like if we have a continuous function, and we can say that if f has a finite number of jump discontinuity, we still can integrate, and then we say that f is integrable on the interval AB, and we need to include AB because we want to calculate through whole area. So the definite integral exists, and how it exists, basically through this limit, and then we can calculate the delta and the x for every point that we set up. And this xi will determine what kind of method we are going to use. So we have approximation. So we can have approximation here. So we can approx, which we call the Riemann sum. So basically, Riemann sum has at least two methods: the right endpoint and the left endpoint. Similar to what we have in the early introductions. So what does it mean is it will affect this formulation. So if you take the right endpoint, you set up the points on the right, on the rectangle. Okay? So if you have maybe the graph is like this, or maybe not too, maybe a little bit, maybe just like that. Okay, just to make it easy. So we can make, for example, this is the rectangle, and all the rectangle touching the right side of the rectangle touching the curve. Okay. And we say that this will be our first x, or a. So a and then delta x. So a plus delta x. This will be maybe we say this is some number, and then plus delta x, plus delta x, plus delta x. So it will depend on what kind of method we are using, and we can think which a we are going to use, okay, which a, and then it will affect the whole formulation and the calculation. Okay, and if we take for example, the left endpoint, for example, if you take the left endpoint, let's say we have the same or similar graph. So maybe let's start from this bottom side here. Okay. Well, we could say this one here, or sometimes the left endpoint in certain point, or right endpoint, sometimes they will lose the first rectangle, or maybe you can start from the other one. It depends on the rectangle. Okay. So we take this, okay, and this, okay, as our x1, x2, x3, x4. Okay. So that is how we can calculate, and basically we calculate, like for example, ON is 10, which means this will be the endpoints, the differences divided by 10, that is how many we have, or the delta. And then we can set up x1 is 1, x2 is 1, 3 until x10. And then we multiply the area. Okay, basically area 1, area 2, area 3, and then we plus all of them, and then we put inside here, which we just focus on the sum. Okay? We just focus on the sum. It's not yet a limit. So this is this is actually a numerical method. We focus on computation of the rectangle only. Okay. So this is we say numerical method. Okay. Now we have right endpoint, left endpoint. Now the third one we call the middle point or midpoint rule. The difference is just this, okay, the xi. So we set the rectangle to touch the curve at the middle, okay, in the middle part. So we multiply with 1/2. The rest the same. Okay, the rest is the same. So we focus on calculating the sum, and then we can factorize the delta x, and then we just plus all the height, the function, okay, with x1, 2, 3, x until n. It depends on what we are going to approach, whether maybe 10 rectangles or 15 rectangles, okay, and then we plus all of them. Okay. Like for example, we have here, use midpoint with n equal 5. So we could start with taking the so we start from a equal 1 and then b equal 2. So delta x will be 1/5, right? Or let me write 2 minus 1/5 or 1/5. So that's delta x. So every plus delta x, that will be our x1, x2, x3, okay? So we can start with 1 and then plus the, or maybe let me write with the sequencing. So 1, 1, or maybe let me write this xi is half. Let me write the formulations plus xi. So since delta x is 1/5, so we are going to see that if the endpoint is 1, so 1 to 1.2, so half, or maybe let me write here, the downside here. So x1 is half, maybe I would change this, half 1 plus 1 plus 0.2, right? Right, yeah. So 2.2 divided by 2, 1.1. Okay, and then we set up for all the midpoints, x1, x2, x3, we can get 1.1, 1.3, 1.5, we can just add 0.2, 1.7, and maybe nearby the 2 is 1.9. So 1, 2, 3, 4, 5. So n is 5. So x1, x2, x3, x4, x5. Okay, so we can write this. It's approximate with the midpoint delta x, and then adding all 1 plus 1.1 plus 1.3 plus 1.5 plus 1.7. Basically, the left endpoint and right endpoint also similar method, okay? But the difference is just the x1, x2, x3. For the midpoint, we need to set up the middle point in the rectangle. So basically, we are taking this, okay, taking 1.1 into the function 1/x, all, and then plus. And I think you need calculators to do this to get it more clear number. So 1/5, this will be 1. And if somehow this is going to be in exam, I don't think calculation until the end is very clear. I think if needed to approach using some numerical method, if you work until here, it's okay. Okay, you work until here is okay, and no need to calculate until the end. But in the real case, you need to calculate to get the numbers. But if you just need to show how the methods work, this is okay. This is okay. Just to see what is the delta x, what is the function, and then still okay. For me, it's okay. Sometimes I don't see like calculation until the very end is really proving something. But I think if you have the good process, I think you can stop until there. But if you want to calculate, this will be approximate around 0.691. Okay. Okay, now this is approximation. So we have left endpoint, right endpoint, midpoint rule. There will be another set of numerical methods that maybe we are going to learn, but the very basic part is this three methods: okay? Left endpoint, right endpoint, and midpoint. And I would like to move to this property of integral. So if we have a constant and we have the integrations, it means that we can basically, I think if you know how to get into the constant, okay. So remember that if we reverse in antiderivative, before we have a constant, there will be some variable, at least variable, or this one is x, because it's dx with respect to x, the variable. So x we put here, so which we can substitute with b and a. So it becomes b minus a. Okay. And the rest of it, I believe, it's quite intuitive. So if we have like, if we can separate like from big function become two, like maybe like a big fraction and become two, like your exam. What's the function? This one, right? We can separate become this, right? And easier to derive. Many derive like with the whole functions. I think if you derive like each one of them, easier, and then you can combine later to see the property of the first derivative and second derivative. Right? So if you can make separate like that, we can also separate the integration. Okay. And every constant we can factorize because it's meaningless in the integration because it's only affected the variables. Okay. And then if you subtract, of course, the same with the if you add, and then we can separate all together. And the most interesting is this number 5 property, which we can separate the interval. Okay, so we can separate it. So if we can get through here, so this a to b, if we know any number c in between the curve, we can set up a c and then c b. Okay. So how to visualize this and to logically remembering it to make it more sense is basically we have this curve, and then we have a, b interval, and we have c in between. So it means that we are compute integration from a to c plus from c to b. Okay. Somehow this for the next chapter in integral, especially finding the area and volume, this method, this property, I think will be very useful. Okay, sometimes you cannot really integrate all directly, so you need to separate one by one to get more simplified method each time you integrate. Okay, so we can have some separations like that. Okay, like for example, if we have, so let me write here example. So it's the same function f. Now if we would like to find from 8 to 10, now we can take this and we can break down and combine it like this to get the whole from 0 to 10, which basically we can get this minus this. Okay. So it will be 17 minus 12, it's 5. Okay, just to get to know the property. Okay, now another property that is, I think, somewhat interesting is the comparison property. So let me write here, make it a little bit big. So comparison. So if we have a function, we know the function, we know the endpoint a from A to B, and we know that it is a positive function. So we know this positive function so that our arguments will be valid arguments. And then we have another function which is g, and we say that the function of f, which we define under the first one, is bigger or greater than the g, and then we also set up the interval, the same interval. Then the integration of f, it should be greater than g. Okay. And then we can also compare the functions with some values, which we know that the values is between this small m and this capital M, which we could see that this function in the middle, or the integration in total, is in between this m multiplied with the b minus a, which is the interval, and also in between this the capital M with b minus a. So to get this to get these expressions of this comparison, we could start with looking at this graph, and we set some points here. So let's say this is our f, and this f is in between this small m and the capital M. So we could see that the f is in between those two values. Okay, so f is between this and that. Okay, and then we take the integrations. So take integrations, or maybe let me write the new one. So integrations from A to B. This also the same m dx, m dx. So this will be m b minus a and we need to make sure that the f is a positive function. Okay, now basically all the introductory for the definite integral is finished. I would like to move a little bit for introduction to the next section, which we call this as a fundamental theorem of calculus. I think I will move to the new slide. So, fundamental theorem of calculus. Okay, so the first part of this theorem, we are going to deal with, so the first part, we are going to deal with a function, let's say g, is an integration, and we are introducing a new variable t. So we are going to integrate this from a constant a to variable x. So in visuals, this means that if we have, let's say, a graph like that, let's say this is y is function of t, and this is a, b, and then we have some x, which is x can be anywhere between a and b. And now we are going to rewrite the area as function g. Okay, so basically it says that we can rewrite the integration or the area here as a function, which we describe this function as integration from a constant a to our variable x with this the function f. Okay? So it becomes a function of x for g. So we say that the f is continuous on a interval AB, and x is varies between a and b. And we say also the g, or g of x, is continuous on AB, or maybe let's write with the green, and differentiable. Remember, if we are talking about differentiable, we are not going to include the endpoint, so we need to write interval with the open bracket like this. Okay. And the conclusions from these two statements, from f and g, from that formula on the first part, we can write g prime x is equal f of x. Or if we would like to make step by step, so g, we can say that g of x is antiderivative of f and differentiable, so that if we have g like this, an integration f of t dt, we can take this, both of them, derive each one of them, this will be g prime x, this will be f of x. So we can see that every continuous function f has antiderivative g. Sometimes maybe because the previous one we say antiderivative with the capital F, you can write with the capital F if you want, like if you want to define this with a capital F like that, is also okay. So this is the first part. So from here, from the every continuous function has antiderivative g, this is linking the derivative to the integral. So that's why we call this a fundamental theorem, because it's going to connect the derivative that we have done to the integrals. Okay, maybe I will just write the second part on the same page. Okay, so this is the first part. Second part, maybe let me wait if you want to write the notes here. I think it's okay if you want to replace g with f, the capital F like that. It's okay. It means the same. I will write here f is g. So you can write with capital F, because sometimes capital F make it easier, because you can think like from the capital F and then you derive and it becomes smaller. Maybe it's better. If g, maybe it's more different function, but if you capital F, oh, the same F. When I was learning before, I was thinking of it. It's easier, like from big capital and then oh, you derive and it becomes small. Okay. So the derivative and integrals. Okay. The second part is we call the net theorem. Okay, the net theorem. So the second part. So let me just write again. This is the information that if f continues on the interval a, b, and then the integrations of this f, we can write as, let me write with the capital F, okay? Like in your textbook, it's G, but I would like to write with F. So F, the capital F is antiderivative of this small f. So again, the f prime is f, or f prime x is f of x. Now this method or this statement is we call the net theorem. So basically we are taking the numbers inside the antiderivative and then evaluate them. Okay, the next sections is just some proving and some proving, and then we can have your midterm score. Okay, just one more page, I think. One more page. Okay. Okay, the next part will be some proving on this, at least the fundamental theorem, so that you can see that how we could get that the conclusions. Okay, so suppose that the f is continuous on the interval, which means that this is the interval, if the f is this, and then the f prime x is this. So we say the f is continuous on AB. This is the same, just introductory. You don't need to write this. The same as before. Okay, so as a conclusion, if x and x plus h, okay, h is the distance you observe, okay, on interval AB. Now if we take f x plus h minus f x equal, this will be a to x plus h ft dt minus, this is a x ft dt. Okay, based on one by one. Okay, so antiderivative, this one, the f capital F, this is the area, right? The area from a to x plus h. This one is this one. Okay. So let's expand the integrations. Okay. So I would like to separate the area. So this A, I would like to stop until x. And then from x, I would continue to x plus h. This is the first part, right? From our separations. And then we have minus. I will move a little bit. So minus, the rest is a x ft dt. Now we could see that this part, this two, is the same. So we can cancel this, right? So at the end of the day, we have this. Which we have proven at the beginning. And then we divide with h. We multiply with 1 over h. So let me write here, multiply with 1 over h. Both of them. So the left will be over h. And we have 1 over h. And then x plus h, ft dt. Let's name this the equation 1. Okay. So assume h is positive. Okay, to simplify our equations. So f continues on the interval to make our statement correct. We are going to use this equation later on. Okay. Okay, let me copy this and move to the next page. Okay, maybe wait if you want to write first. Okay. Now, let me copy here. Okay. Now this is what we call, the next part is the extreme value theorem. Okay, let me write first. So suppose there are u, v on the interval x to x plus h, which if we use that u and v, this will result m. We call this is the minimum value. And if we plug in the other one, this will be capital M, which is the max value. And from comparison theorem, we can divide this small m and capital M in between. The f of x is in between the m, okay? Which means this is very similar to what we have before. So let's say this is small m, and let's say this is the capital M, and our functions is maybe here. Maybe that is the f of x, or the f of x. Okay. And basically this is u and v, so we plug in u and this is the v. And suppose this is the x-axis. Okay, now similarly, from the comparison theorem, we know that this will be in between. So we integrate both of, or all the components. So let me write here, so integrate with the x. So now we change this a, b minus a to x and x plus h, okay? So a become x, and this is x plus h. This is f of t now. And b minus a means that x plus h minus x. So it's just h, right? So this will be m, h, and capital M, h. What I want to do is I will multiply all this with 1 over h. And h is the positive numbers. Okay. So now we have m less equal 1 over h. Okay, let me finish this part and then I will give you the score. Okay, okay, so m is our function of u right here, from this one. Then the capital M is function of v. So let's change to that functions. So this part on the middle, this will be equal to this, right? To the left part. So this will be f x plus h so this is f of u, this is f of v. And then as h closer to 0, we can say that limit as h getting closer to 0 so as h getting close to 0, then u will be getting close to x and v getting closer to x, which means by squeeze theorem in limit, right? So if we know the left side limit and the right hand limit, then the in between of them should be also equal. So then limit as h getting closer to 0 of all this this will be equal to f of x, which include what we have say before, that this will be coming true. Maybe to make it better, this part, we can say that limit h to 0 of f of u is basically limit u to x of fu. So this is f of x. And the same thing with the v. Or maybe let me write over here. Okay, so we'll write one more conclusions. Let me make it smaller. So conclusion is, if we have this equation, so if we integrate and differentiate or this is ddx, we will go back to f. Okay, that's it. Okay, that's number 2. And then number 3. Number 3 is basically we can let all of this become any y, g, or anything. Take ln, and this 1 over x becomes here, and we get the structure. Or you can think like if you get this and then you take limit, what will happen? I think this will be indeterminate forms. So when this is the indeterminate forms, we can make forcing the x like this, so we get the 0 over 0 situation, which we can completely go for L'Hopital rule. And some of you, the mistake are here, this part. You get the ln correct, but here it needs to be quotient rule. Okay? Quotient rule. So we have the square here, which we can cancel, and then solving this become 2a over a minus x. Then we can put the 0, so we get that this will be 2 over a. And don't stop here. We need to define the y. This is ln, so we need to take y. So it will be e with the power of 2 over a. Okay. And then the number 4. Okay, number 4. I think, as I mentioned, I think before the midterm, I gave you the similar question, not the same but similar. We have the power like this, y to the power of x, or x to the power of y. Anytime we have that kind of definition, you can clearly separate this, calculate in the different side of paper, like this. You can take this as f. Our goal is finding this derivative. Okay, this derivative is actually, oh, maybe I forgot the bracket. Yeah, like that. And then we put back this f prime into our equation, which is here. And as I mentioned in the midterm, you don't need to express until the dy dx equals something. You can just express it as it is to manage your time wise. So we can just derive this, and then I think we can end until there. I think another approach that I think some of the students make, I think I agree. We can also write like from here. We can move to the right side and then take ln. But here, when you take ln, don't forget to derive this, and don't forget to do the chain rule. Okay. It's also correct, I think. But if you take the ln directly, like here, so let me write. So you take ln on the right, on the left. I think most mistake is here. You take ln, and then you take, and then you divide, and it makes this into ln yx plus. Okay, this is wrong. Okay, cannot, right? You can do this if this is multiplication. Okay. Somehow, I think a few students take that approach, and miraculously you get the same correct answer. So I still give some like a point from there, but that's not true. It's not valid. It's not valid. So from this expression, we can put all the numbers 1 and e. We put all together, we get the negative 3e, and then this is our tangent line. Okay, that's number 4. Okay. Okay, number 5. I think this is interesting. Usually, you know this, and then usually it's asking the height, right? So we get that we have the rate for when it's going down, and then the rate when it's away, and we need to input the value when x is 4. When x is 4. So we know that this is a Pythagorean formula from the triangle. What we need to remember is the L is a constant. If you take this as derivative, it means that the ladder You can change the whole time. Okay. So we need to make sure that the ladder is always fixed. Which means when we derive that, it will be 0. Okay? Do you get the logic?
Yeah.
So the ladder is constant. So we take that derivative as 0. So from here we get y. From here we get y. So y is I think 8, right? From there we get y, which is 8. So when x equals 4, y equals 8, we can just use this factorial again, and we get 4 square root of 5. Okay. There are also alternative methods, at least 4 methods to get this 4 square root of 5, but I think too much if I put inside. I think some of you maybe take some different approach and get the same result. I think it's okay. It's okay. And then the number b. Mostly, since you don't get the a correct, number b also not correct. So what we need to do is we need to take the angle as our variable, and also we need to take the x and y as our variable also. Okay? The one that fixed is just the L, right? So we need something to relate this L. So either x over L or y over L. So either sine or cosine. Okay? So we get the cosine here, which is the x over 5 square root of 4 square root of 5. We derive, solve, and then we get all the input. We get that this is going to be 1 over 40. You get negative or positive, it doesn't matter. I write negative because I assume the first part of it as a negative 0.1 because I assume that everything that is decreased in length will be negative. You can say it's positive, it's okay. The conclusion will be the same as long as you have the consistent definitions. Okay. And then we can also take the sine, which we still get negative 1 over 40 because I take the dy over dt is decreasing, which is negative. So it's still the same 1 over 40. So that's the related rates. Okay. Okay, the next is, I think this is supposed to be simple. So the idea of the approximations is basically every time you have an unknown function or unknown like result from some numbers like this, 100.5, 28, 29 degree. So the first thing we need to remember, if we try to take the square root, the number that is easy to be square root, that is the one that we are going to approximate from. Okay. So the easiest one is 100, right? And then we let this, and we can imagine that the function is square root of x. So basically, we can get that the f of x is f of a plus f prime a, and I would like to write delta x, okay, to avoid mistake when it's negative or positive. Okay, so to get you the correct idea, because sometimes students make mistake here. So I need you to use logic. Okay, we have 100.5. We start from 100, so we add more, right? This will be positive. Right? The difference between 100 and 100.5 is just 0.5. So we take 0.5 positive, right? So we take A is 100, but I think you have confusion here. But the idea is we take function at the nearby point that's easy to count, which is the 100 put here. So this will be 100.5. This is 100 plus f prime 100. and the delta x is just 0.5. And then plug in all as it is. The f prime is 1 over 2 square root of x. This is 1 over 20. And then multiply with 0.5. So you get 10 plus 1 over 1 for 100. And if you add up to here, it's okay. If you want to combine, it's okay. If you want to make it decimals, also up to you. Now the second one, the cosine 29. The value that we are available to calculate is 30. Right? So it becomes less, which means the delta will be negative. Okay, negative 1. Okay, I hope that's clear because by logical sense. Because sometimes you maybe mix between positive or negative. So the same thing, we take g prime, but since g prime is negative, we get positive at the end. Okay? So negative, negative. Some of you still write in 1 over 2 and then combine it still okay. This is I just write in the in radian angle. But if you write here, I still give you like full points, okay? So that's number 6, okay? Number 6. And number 7, okay? So you have a function x minus 1 over x squared, and we have a lot of questions. State the domain. I think that is going to be easy. So it's only not equal 0, and the whole interval will be valid, right? So we can write domain like that. And then for even or odd, we check negative x, put inside, and I think it's not going to be the negative part of the function, which means it's neither even or odd. So we can just write neither. And the asymptotes. First is our obvious choices are we take the limit as x approaching 0. Then we see that it's going to be getting infinite value, which this is going to be vertical asymptote. I think most of you, not most of you, I think half of you write the vertical asymptote equal to 0. What is the line? What is the line? You need to write x equals 0. That is the line. Okay. Do not write vertical asymptote equal to 0. It's meaningless. Okay. The second part, we take the x closer to infinity or negative infinity, which we can conclude directly if you see the function here. The top equation on the 1 degree. This is the second degree, right? The square and this 1. So you can see that it should obviously going to be 0. Or if you want to prove, take divide by x squared, this becomes 1 over x, negative 1 over x squared, this becomes 0, and this becomes 0. Okay. Same thing with the negative infinity, is also 0. I think it doesn't matter. So why I'm writing vertical? It's horizontal. So y equals 0 is horizontal asymptote. And after all that statement, we can take the first derivative and second derivative. To make your life easier, we can separate this, right? And derive each one. Easy, right? I think most of you are like, wow. I saw like, wow, and then, okay, continue, jayo. Okay, I think this is I think my suggestion. Every time you have fractions and you think you can separate, derive, and at the end you can combine. Okay? You can combine like this. Okay? So only 2 lines. And check the test. So you have 0 here. Why I'm put 0 here? Because we know that this is asymptote. So it will affect our graph, right? So we put here 0 and 2. So we take this equal 0, we get 2. So we check the point, negative, positive, negative. Okay, we get the increased interval, the decreased interval, okay, from this evaluation. And we say that this is critical point, and we have the maximum value is this, and or you can write the 0.2 and then 1/4. It's okay. And then from the G prime, that is separate like this. Again, very easy, right? Okay. So G double prime, we get, and then we can combine them together, we get this. And from that second derivative, we also can get this number. And remember the 0, I put 0 here because we know that this is asymptote and it will affect our graph. We put interval, and interestingly, we have negative, negative, positive. Okay, so we have the concave downwards here and concave upwards here. But since it's asymptote, so this should be not going to have a continuous function in this part, right? It's not continuous here. But we still write first the concave downward upward, or if you just write this part and then say it's concave, it's okay, it's clear. And we say the inflection point is x equals 3. I forgot to write the intercept. If you want to check the intercept, it's going to be x equal 1 because that is make the functions 0. So it should be, so the function should be crossing the x equal 1. So to make sure that we are going to graph the curve correctly. And then we can draw the curve. Maybe it's not really clear. This should be a little bit maybe smoother like that. But as long as you mention it's like from upwards and then this is downwards. Why is it upwards? It's downwards. And we know this is decrease and then increase and then decrease. And we know that this is the local max. But then we have, oh, why this is 3 here? Should be around here. Maybe I will make it longer. Should be okay, maybe like that. Maybe not really smooth, but as long as you mention the inflection point there. So this is inflection point. I think still okay. Okay, that's it. So make up exam, just A, okay, just A. Optional, if you want to come, you can come. If you don't want, it's okay. Up to you. Topics were the same. Maybe I will make simpler, but not easier. Not easier, but simpler. I know. I hope you know what I mean. Not easier, but simpler. Maybe the question more direct. Okay, I will put all the answer key later on. Okay. So I think that's it for today's class. Okay. So I think